I posted an assignment. Did you see? Did anyone of you see that? I posted some assignments. Did you see that? No. I posted a new set of assignment. New set of assignment, not quiz. Okay. What is it? Whatever you haven't done, you submit it. That's different for the. Yeah. If you can submit, it's up to him. You can submit. No problem. Yeah, you can submit if you have. I mean, if your answer is not right, you submit it and let's see. He will decide on that. I will not decide on that. You ask him. Okay, anyway, this is to inform you. I posted a new set of assignment, and it's better you submit it before midterm. You can I mean, I have given. I mean, that's the deadline I have set, but I think it will accept after midterm also. I mean, around 7 or 8 of March. But it's better you submit before midterm so that it will be a practice problem. Yeah, that also you submit with that. Yeah, with this. Yeah. Do you have like a list of it? No. You are supposed to have noted it. Yeah, there are only 3 in the first class. Yeah, that's all. I didn't give anything after that. There was not much occasion to do that. Okay. So we were discussing expectation, variance, and all those things. Moments. We were discussing moments, and centralized second moment is what is called variance. And we observed, it's not a proof, if E of mod x power k is less than infinity, if the kth moment exists, then E of mod x power r is less than infinity for all r less than or equal. Maybe you can take it integer or non-integer, doesn't matter. It's true. We proved it for integer, and that's enough for us, for our purpose. Okay. But incidentally, I think I made a mistake last time. I said that xr is less than or equal to minimum. It should be maximum, right? Maximum of mod x. Right? It should be maximum. I said minimum, I think. Maximum also works. I mean, the inequality works for maximum and minimum. Minimum certainly works, but it is a maximum. That's what I should have said. I think I said minimum. So anyway, the example is another example for the, so, and variance is defined like this. Variance of x is E of x minus ex square, which is same as ex square minus ex whole square. And here is an example where x is x such that ex is less than infinity, but variance of x is equal to infinity. Okay, and it's very easy to define. We have already seen an example. I mean, if you have f of n, I mean, so when I said random variable, I only have to define the mass function, probability mass function. We have seen that this is a mass function and which has expectation infinity. Okay, that's because you have, I mean, this is a mass function. When you add it, it adds up to 1. So because you have n square, the degree is 2 here. If you for the expectation, you will multiply by n and then sum it, but the degree will become 1 in the denominator. So that will be infinity. So here I have another n plus 2. Okay, then this will have the first moment, which is expectation, and the variance will be infinity. And for this to sum to infinity, you need a c here. You can find the c very easily. Okay, let us just sum it. Summation of n into n plus 1 into n plus 2. You know the answer. You can tell me if you know the answer. Otherwise, this is going to be 1 by n plus 1, 1 by n plus 2, which is, if I multiply that, 1 by 2 into 1 by n minus 1 by n plus 2, then minus 1 by n plus 1 minus 1 by n. Now, this will be, there is a half here. This will be 1 minus 1 by 3 plus 1 by 2. So it will go on. Other things will cancel. You don't have to worry. Similarly, this will be 1 minus 1 by 1 by 2 minus 1 by 3. Then all the other things will cancel. Okay. So what will you get? So you will get 1 by 3 will cancel here. 1 minus 1 by 2 is 1 plus 1 by 2. So that is 3 by 2, 3 by 4, is it? Yeah, it's 3 by 4 minus only half, which is 1 by 4. So this implies that C should be 4, right? Okay. So the density is this. F of n equal to 4 by n into n plus 1 into n plus 2. This is a mass function. And if you, so expectation is finite, of course, we just summed it. So E of mod x will be 4 summation 4 by n plus 1 into n plus 2. We just summed it. So you know the answer. You can find it. But E of mod x square will be, so you need n square, which will be 4 by n plus 1 into n plus 2. I mean, sum of this, n equal to, it will start from 1, right? 1 to infinity. And this is greater than, you can, no, wait, what is that? No, this is not correct, no? N here, there is a n here, only n will cancel. So I have this 1 plus 1 by n. This is greater than 4 by 2 into, okay. I think it's okay. So you have an example where, what's the fun? What happened? Said that? I don't need audience through this. Okay. If you are interested, you come to the class. But I may give the quiz so that there is an incentive for people attending the class. That's all. Okay. I don't want to give marks just for attending the class. I will give the quiz. Next time when I give the quiz, I will lock the door anyway. So first, that is just for. Okay. Okay. So now let's consider sum of random variables. I mean, if these things are easy and you know it, it's okay. But there will be some minor points which will in the class and which will be used in the exam, and you may miss it. Okay, that's all. Okay. What is it? There is a summation somewhere. There. Sum is here, no? Sum is dot. That's right. Yeah. Yeah. I sorry. There's a sum there. No, there is no sum here, right? Here they get cancelled. Yeah, they just cancel only the non-cancelling terms. I have grouped it. Okay. So now let's consider sum of independent random variable. Sum of random variables and independent random. Sum of random variables. So if we have some, let's consider two random variables. Okay, then we consider the variance of that, because we want to talk about covariance. Okay, variance of x plus y equal to E of x plus y minus E of x plus y whole square. And that is same as E of x minus Ex, y minus Ey. You can just group it. And it will become E of x minus Ex whole square plus E of y minus Ey whole square minus 2 times E of x minus Ex into y minus Ey. Right? Just A plus B whole square formula. So, yeah, sorry, A minus B, A plus B whole square formula. Correct. It's an A minus B. So, okay. X minus Ex, y minus Ey. I'm just applying. I just did. Okay. So this is just equal to variance of x plus variance of y minus 2 into, I call this term as covariance of x and y. Okay. Covariance of x and y is nothing. It is defined to be this. Of course, when x equal to y, it is just the variance of y minus ey. If you expand it and do the same computation which you have done for variance, this will be exy minus ex times ey. Okay. Exy, If you take this ex is a constant, so it will be just ey. And here, if you take ex and ey is a constant, you will get this. And there are three of them. One of them will cancel. This will become positive. So, yeah, okay. So this is what is called covariance. Okay, this measures the dependency in some sense, but we will give a counter example that covariance equal to 0 doesn't mean they are independent. We will give a counter example. So this is something. If covariance is 0, there may be definition. If you have two random variables such that covariance xy equals 0, then we say x and y are, we say, I'm not writing it, x and y are uncorrelated. Okay. Okay, let's see. So in particular, corollary, it's not a, just a remark. Yeah, multiple correlation matrix. Yeah, that's called covariant matrix.
No correlation. They say X and Y are correlated or uncorrelated.
Yeah.
Many people are uncorrelated.
Yeah, this is one way of saying it. I'm just saying this is the definition. Yeah. But what is the other way? Eh? No, we are not considering. We define this as uncorrelated. We are not going into all that. See, there will be many inequalities. There are so many things in probability. We will not do all of them. Okay. We will, for example, we will prove something called Chebyshev inequality. There are many inequalities which improves that and other things. We don't have time to do all that. So we'll do only one of them. So this is what we call as, this is one way of saying. Okay. There are many things. There are so many things in literature. You can. Okay. So this is not corollary. This is just. Oh no. Don't do this again. Okay. Okay. What was I saying? So this is just a remark, which is, we didn't prove anything to say the solid is corollary. So, so similarly, if you have, so this is also true. If you have n of them, okay, I'll write there. We have n random variables, then variance of summation xi. To do the same thing, you group it, there will be two of them. So this is just summation of variance of xi, I equal to 1 to n, I equal to n. And then you have the same thing. 2 into. So here you have to sum it, you have to take all ij. You can just write ij such that covariant of xi, xj. You can just do that, or you can write it as I equal to 1 to n minus 1 summation j equal to, start from I to n covariance of xi. So in particular, they are all independent, then the variance adds up. Okay. So if they are independent, the variance adds up. So in particular example, binomial, parameter n and p. So you have a binomial distribution with parameter n and p. Okay. So if x is binomial with n and p, then x is equal to x1 plus up to xn, summation xi, where each xi is Bernoulli. with parameter p. Okay. Then E of xi, we have already seen E of xi is p, and E of x is equal to n times p. Similarly, variance of x equal to summation variance of xi, and variance of xi. I think we have seen this. Variance of xi is, I mean, ex square and ex square minus ex, exi square minus exi, but exi square is exi, which is, I mean, there is only one value, 0 and 1. So it will be just p. And here it will be, this is already p. So p minus p square, which is p into 1 minus p. So is equal to p into 1 minus p. So p minus p. So what I have said, ex square, which is p, and what did I write? Variance of, yeah, variance of xi is just, this is what I have. Which is equal to n times p into 1 minus. Okay. So this is the variance of binomial. Now we want to do, so this is easy, I believe. So, okay, this is okay. Now we will do carefully, compute the, I have already said about mean, but I think I didn't explain something. So we will do carefully, the way, compute the variance of hypergeometric distribution carefully. What is hypergeometric distribution? You have n objects, okay, and n are of type 1, and n minus n are type 2. There are two types, and you choose k. Choose k of them. Okay. Then the random variable s is number of type 1 objects. In k times, you choose k of the number of type 1 objects. Okay. So you draw k times. So xi equal to 1 to k, and we know the probability. I mean, we don't need this. I'm just writing it. I mean, here we do the computation using those formulas, so we don't need it. Probability of x equal to k, we have already seen, which is n choose k, right? N choose k, and no, among n we have n type. We choose k, correct. What numerator? We are choosing n k, among that n k, and n minus n minus k, right? N objects are there, we are choosing k object. This is the total possibilities. Among this n, the type, this is the type 1 possibility, this is the type 2 possibility. This is correct. Huh? So think about it. There are total n objects, right? Okay, you are choosing k objects. So this is the total number of possibilities. Okay. What is R? There is no R. Oh, sorry. Oh, sorry. You are right. N equal to I. Sorry. N equal to I. So here it should be R. I'm sorry. I have written k there. No, x equal to R equal to n choose R n n. So here it should be numerator n minus n. Wait a minute. N minus n. Wait. N minus n. Then n minus R. K minus R. Sorry. Yeah, you are right. Yeah, this is correct. Yeah, these things are confusing. Yeah, now it's okay. You tell me. Now it's okay. Okay, this is right. No, I forgot the R. I was talking about, okay. There are n, you are choosing k of them. Okay. Then among this n, I mean, we want x equal to R. So n R and n minus n, k minus R. So we will do it carefully, but we don't need this. I want to write this x as sum of n Bernoulli random variables. Okay. So let xi equals to 1 if type 1 object is selected in the ith draw. Okay. in the ith draw, selected in I, and otherwise, if 0, otherwise. Okay. This is a 0, 1 random variable. Xi is a 0, 1 random variable. It takes value 1. If in the ith draw, we have selected type 1. Okay. So this has only, this is Bernoulli random variable, clearly, of course. It has only 2 choices, so that's what Bernoulli is. Okay. So we want to compute the probability, and probability of Xi equal to 1. I mean, this is the claim. I used it last time, but I mean, this was very similar to what we have done in Polya's scheme and some other card, taking out this card. And I mean, we remember that the probability doesn't change if you do the experiment, even though they are dependent. I mean, this is with replacement, right? You take something and, sorry, without replacement, right? So probability of Xi equal to 1, the claim is Xi equal to 1 is n by n. This is the claim. Okay. Okay. So how do you prove this? Can anyone tell me? You have already. Eh? Out of n objects? Yeah. No, it's not like that. You have already chosen something, no, earlier. Ith draw, you have already chosen I minus 1 things. So why is it n by n? So it is clear that we prove this by induction. Okay. I'm saying that in the hypergeometric distribution, x is the sum of xi, where xi is equal to 1. If in the ith draw, you get the type 1 objects. It's 0 if it is type 2 object. Okay. So now I am saying that probability of xi equal to 1 is n by n. Okay. So clearly, probability of x1 equal to 1 is n by n, of course. You haven't done anything. So there are n objects, you are choosing n. Okay. Now assume, this is induction hypothesis. Assume P of xi equal to 1 equal to, I mean, of course, xi equal to 0 is 1 minus that, that's clear. Okay. Is also n by n. For all, I mean, this you are assuming, I mean, this is an induction hypothesis for all n, for all k. Okay. Because x1 equal to 1, n by n for all, that is the induction hypothesis. X1 equal to x1 equal to 1, this is true for all n and n. So you assume the induction hypothesis, probability of xi equal to n for all n and n, small n, big n. You are assuming this is your induction hypothesis. Okay. Then we want to compute. Let me write it here itself. Okay. Now you want to compute probability of xi plus 1 equal to 1. Okay. This you want to compute. That is equal to, let me use P, okay? P of plus. Probability of xi plus 1 equal to 1. So this is xi plus 1 equal to 1. Given xi equal to 1, then P of xi equal to 1. Plus probability of xi plus 1 equal to 1. Given xi equal to 0, okay, times P of xi equal to 0. Huh? What? Yeah. Okay. So when xi equal to 1, okay, so let me first write it. Xi equal to 1, that has probability n by n, by induction hypothesis. I'm just writing this term, probability of xi equal to 1. Okay. That I'm writing it as n by n. Okay. So okay, maybe I will write it here, n by n. Okay. What is the probability of xi plus 1 equal to 1 given xi equal to 1? Xi equal to 1. Okay. Then there are I choices, right? So I mean, I mean, you have chosen, I mean, you have fixed one, which is one. So there are n minus one chances, and you have n of, right? N minus one. This is given xi equal to 1, xi plus 1 equal to 1 is a I mean, is something like you have n minus 1 number of things and you are choosing n minus 1 of type 1, which is there, right? So this is this. You have total number of objects is n minus 1 now. If you fix xi, I mean, the ith term is 1, ith result is 1. Okay, you have n minus 1 objects. Out of that, you are choosing n minus 1 objects. So which you are assuming, this is like, I mean, we are using the induction hypothesis again. Here n is n minus 1, n is n minus 1, and I is, okay, I is I. Okay, for I it is true. Okay, so because of that, this is true. Similarly, another one is, so, and P of xi equal to 0, that is n minus n by n. Okay, and so here we have, yeah, this is n by n minus 1. Right? It's clear? Yeah, let me repeat. So this formula is okay. Conditional expectation is okay. Okay. So this is probability of, this is induction hypothesis, probability xi equal to this. So those things I have written here. So given xi equal to 1, okay, there are I plus 1 raw now. There are I plus, you are choosing I plus 1 objects. Okay, ith object is fixed. So you are actually choosing I objects from n minus 1 objects. Okay, and there are n minus 1 type 1 because this is given as type 1. So there are n minus 1 type 1 objects. So which is n minus 1 by n minus 1. Here you are saying the ith object is 0. Ith result is 0 means it is of type 2. So there are n minus 1 objects. You are choosing n, I mean, there are n type 1. So the probability by the, again by the induction, both these things are by induction hypothesis. Okay, this is also by induction hypothesis. This is also induction hypothesis. All these things are by the induction hypothesis. Induction hypothesis is something which you are assuming for all n and k. So this I should have done carefully, but this is very similar to what we have done in Polya's on scheme and another using cards. We did something, but we did for one or two draws. But what I don't remember what we did. But this is very, probability doesn't change, even though they are dependent. They don't change. Yeah, yeah, correct. So I mean, probability, we have to compute it, then only we will know. So this is n into n minus 1. Okay, this is n square minus n plus nn minus n square, and which is equal to, and n minus 1 will go n by n. Okay.
So maybe we can also look at it this, that we are arranging type 1 and type 2 objects in a row. And in the row, the ith position should be in the type 1 object.
Why? Ith position will be type 1 object.
So like
you are arranging one after the other. There is no arrangement involved. Why are you saying that?
I'm constructing like that. I'm constructing a sequence. So suppose we are just taking all the n rows. We want that in the ith row we should have the type 1 object.
Yeah, but why particular arrangement matters? I don't understand. You are arranging it type 1 first and then type 2, something like that.
Type 1, type 2, consider.
Okay.
So in any of these arrangements, in the ith position, if there is a type 1 element.
Correct.
That means that in the ith row you get a type.
Oh, you are arranging it. Okay, you are arranging it and saying that you call it like that. Okay. Instead of choosing, you arrange it like that.
Yeah.
You can do anything. Yeah. You can say it in different ways. That's okay. I think that's what you are saying. I understand correctly. Okay. So by induction we have proved this. Okay. So this says that probability of xi equal to, so this, and E of xi is also n by n, right? Because it is Bernoulli. So E of xi is n by n, and E of x equal to summation E of xi, which is there are k draws, no? So yeah, I equal to 1 to 3, correct. kn by n. Okay. Now let's calculate the variance. But here we have some covariance, so we have to calculate the covariance also. Okay. Now variance of x equal to summation xi, I equal to 1 to k. Each xi, okay, x is the hypergeometric random variable, and it is sum of xi, where each xi is a Bernoulli random variable. Okay. What is your confusion? Okay. And the expectation is linear, so ex is summation exi. Yeah, correct. That has no meaning, no? Yeah, it is exi. I just missed e. Yeah. Okay. Similarly, variance of xi is equal to summation variance of xi, which we know already. What is this? Is Bernoulli, I equal to 1 to k, minus summation. So, I mean, let's calculate the covariance of that. So, this is summation I equal to 1 to k minus 1 into summation j equal to I plus 1 to k. Yeah, it's good. You will correct me, because if you just take a photo, it will not be, nothing will be clear. Yeah. Okay. Now let us calculate the covariance of xi and xj. You have two Bernoulli random variable in this situation, but this is not some independent random variable. They have some dependency. Okay. Now we talk about covariance of xi, xj, which is equal to expectation of xi, xj minus expectation of xi times expectation of x. Okay. So what is expectation of xi as j? That is just that the random variable takes value zeros and ones. Only when both of them are one, there is I mean, there is something. So this is just, no, there's no 1/4. This is n and something. No, we have, it's a Bernoulli, but it's a different Bernoulli. It's not Bernoulli, half Bernoulli. Why are you saying 1/4? Okay. This we know that n, this is just n by n. So n by n into n by n square by n square, right? This is e of xi is n by n. This is also n by n. Okay. And this is probability of xi equal to 1 and xj equal to 1. Okay, that is what this. Okay, and we assume that I is less than j. I mean, that's how we have written I is less than j. This is summation, or you can write this as summation I less than j. Okay? Or all, I mean, that's what I have written. So I is less than j. So xi equal to, so this is just, I mean, so let me just write it. I less than j. Okay. Then this is equal to probability of xi equal to 1. J hasn't happened yet. So that will be n by n. And xi is 1. So this will be n minus 1 by n minus 1, right? Okay. Minus, this is minus, sorry, this is minus n square by n square. Okay. This is n into n minus 1 minus n. This will be I mean, if I make a mistake, then that will reflect in the answer. So you should be able to do this calculation. Okay. So can you just tell me what happens? So this is, here you have n square, here n. So you have to multiply by a, okay. Let's take n by n out. So this is just n minus 1 by n minus 1 into n by n, right? What is the answer? n here minus, no, minus n minus, okay. There are three terms coming. Huh? Where is plus? Here.
The last
Here, yeah, here plus. So this is just n minus n into, I'm getting n square and all. I don't know why I'm getting. Oh, okay. If we use the formula, we get variance of x equal to summation. So there are n of them. There are k of them. Okay. K into each variance of xi is what? N by n into 1 minus n by n, right? This is variance of xi, and there are k of them. Okay. This is okay. And in this sum, I mean, covariance of xi xj is same. I mean, covariance of xi xj is the same for all ij, and there will be 1 plus n, I mean, 1 plus 2 up to n, right? Up to k. So this will be k into k plus 1 by 2 into whatever we have there. I think I will not do this calculation. The point is, if I miss something, that will reflect. So you do this. This is just something you get the right answer. But then you just compare with the Bernoulli. Bernoulli, what happens is I mean, you have the expectation is this, and the variance is n into p into 1 minus p. This is Bernoulli. Okay. Here you will have the same expectation for this. Okay, the variance will differ. Okay, and you can see that the variance will, I mean, variance will be near zero when this n is almost n approaches n, and I mean n is small n is closer to the capital N. Okay, and exactly. So that's what that will reflect it. Yeah, that's right. That's so from that it will follow. And similarly, if you have this k is something very small, then it will be like Bernoulli or something. The variance will be like Bernoulli. So I don't want to do that, but if I make a mistake, it will be a problem. Okay. So I mean, it's very easy. Okay, you can just calculate. You can look at the book. Okay. So we have already calculated for Poisson, negative binomial, and all that. We have already done that using generating function. Incidentally, that's called probability generating function. There is something called moment generating function, which will come later. Okay. Okay. So the next we want to talk about, so independence and covariance. Okay. So this is remark. Okay. X, Y are independent. Then covariance of x and y equal to E of course, x minus Ex, or if you can write it as but since it is independent, this is multiplicative, so this is 0. Okay. So if they are independent, then the covariance is 0. They are uncorrelated. Okay, but the converse is not true. Okay. So this is example. X, Y are independent Bernoulli. Let's just have independent. Let's see what happens. Are independent. Okay. Then you can compute the covariance of independent and identical and same distribution, same density function, mass function. Okay. They have the same mass function. They have the same distribution. Okay. Then covariance of xy equal to no, not covariance of x. Sorry, covariance of x plus y, independence but not I mean, covariance is 0, but they are not independent. X and y are independent. X plus y and x minus y will not be independent.
Oh.
That is the example. Okay. Then I compute the covariance of x plus y and x minus y. Okay. So let us compute it. This is just E of x plus y into x minus y minus E of x plus y into E of x minus y. Okay. Now this is same as E of x square. E of x square minus E of y square, right? X square minus y square, E of x square minus x square. Now minus this will be E of x whole square minus E of y. Okay. If maybe I have to take mod, I think. Not sure. If it is Bernoulli, it doesn't go happen to be 0, no? Then this is just Ex, which is P. This is also P minus P is 0. Oh, this is okay. I mean, if X and Y, they have the same distribution, no? So they are same. So this is 0. Correct, no? This is 0. There's no problem about which one is that. Okay, yeah. X and Y have the same distribution. So this is 0. Okay. So now we have to worry, I mean, whether they are independent. Okay. So now let xy be Bernoulli with some p, 1 minus p, of course, probability. Then we calculate the probability of x plus y equals 0 and x minus y equals 0. Okay. X plus y can be 0 only when both x and y are 0. Okay. Yeah. This can be 0 when both are. So this will be this has probability 1 by 4. And the probability of x plus y equals 0 is 1 by 4. And probability of x minus y equals 0 means they are just same, which is half. So if you multiply, you get 1 by 8, but that you get 1 by 4. Okay, so this is the example. They are not independent. Huh?
If two random variables A and B are independent, the covariance of A plus B equals covariance A plus covariance.
The two random variables are independent, then covariance A plus B. No, there is nothing like that. Variance. Covariance of, there is no. What is covariance of A plus B? What are you asking? Variance of A plus B is variance of A plus variance of B. Yeah. Already I am confused. Don't ask too many questions. Okay. Yeah. Okay. Okay. So this is fine. Is there a problem? So this is okay, I think. You have the covariance that is 0. The calculation is fine. They are not independent. To show they are not independent, I am taking this set. Probability of x plus y. I mean, I want to say that x plus y and x minus y are not independent. So a probability of x plus y equal to 0, x minus y equal to 0. This can happen only when both and x and y are 0. So that has probability 1 by 4. Okay. And this, for this to happen, I mean, they are independent, no? So both x should be equal to 0, y should be equal to 0. That probability is 1 by 4. Probability of x equal to 0 is 1 by 2. Probability of y equal to 0 is 1 by 2. And they are independent. So because of that, this is 1 by 4. Okay. All these arguments are there. This probability of x plus y equal to 0, that can happen only when x equal to 0, y equal to 0. Because they are independent, the probability of x equal to 0 times probability of y equal to 0, which is 1 by 4. This probability is 1 by 2. I mean, it can, there are two possibilities here, x equal to 1, y equal to 1, and x equal to 0, y equal to 0. You add both of them, have 1 by 4 plus 1 by 4 is 1 by 2. Okay. So if you multiply, you get 1 by 8. If you take this is 1 by 4. This is the example. Okay. If you have a problem, you ask me, but you can compute these things. Okay. Very simple. Okay. Okay, what is next? Okay, there is some. So you know about this Cauchy-Schwarz inequality you said, but there is what I mentioned. There is one thing. So I talked about this L2. It is all those random variables. I mean, all x is a random variable, such that E mod x square is finite. Okay? This is a vector space, but then I mean, then you can take an inner product xy equal to E of xy. Okay? You can define this inner product between them. This is inner product, but this is not positive. So if you have inner product of xi, xx equals 0, this does not imply x equal to 0. This just says that E of x square equal to 0. That just says that probability of x equal to 0 is 1. Okay? That's what this says. So you take this L, whatever L let us take it L. Okay. Then you take this L naught, all those x, such that probability of x equal to 0 is 1. Okay. Then you quotient this L by L naught. You call this as L tilde. Okay. On this is a genuine inner product. Okay. Is it okay? I'm saying that you take the vector space or all random variables which are square integrable, which has the second moment. Okay. Then you consider all the random variables which are almost surely 0. That's what we defined as almost surely 0. That is P of x equal to 0 is 1. Probability of x equal to 0 is 1. You know quotienting of vector space? Quotienting of vector space. You know quotienting of equivalence relation? Okay, let's just do that. Huh? Probability of probability of no. It can have some value where the probability is not 0. You have n points something. Okay, and you have probability of this point is 0. Yeah. Yeah, that's what almost surely 0. The random variable as a function is not 0 function, no.
Okay, for non-probable events, there can be another.
Exactly. As a random variable, it's not 0 random variable. It only has the probability. Yeah, but you have to. So this is what a probable event is. I mean, what do you mean by probable event? Yeah. So that is what I am writing mathematically. Okay, you just quotient it with all those 0 random variables, then you get it. Okay, so since you don't know what is equivalence relation, all that, if you have some set, I will quickly go through this. Okay, you have some set, yes. This is something very important which you will equivalence relation. You know quotienting of a vector space and all that. You might have studied, but you haven't done it. You are not done in the class. Okay, let's do it. Okay, it's very easy. Okay, S is a set. Okay, you have an equivalence relation. You know what is equivalence relation? Okay, if it satisfies 3 conditions. Let me remember: x is equivalent to x, x is equivalent to y is equivalent to x, transitivity, and another one is reflexivity, right? No. First one is reflexivity. This is reflexivity, and x is equivalent to y implies y is equivalent to x. Okay, and x is equivalent to y and y is equivalent to z, then x is equivalent to z. Okay, these are the 3 properties, whatever the name it has. Okay, these are the three properties. Okay, so we call this is an equivalence relation. Suppose you have a equivalence relation. Okay, then you collect all the you have the partition. Then S is equal to union of all those. I mean, you just take the partition. X is all those. I mean, this is you represent it as all those y in S such that x is equivalent to y. You just collect all those things. This is an equivalence relation. Because of the properties of this, if x is not equivalent to y, then these sets are disjoint. This gives a partition of this. This is what is a partition of something. Okay, so you denote. I mean, this is a set actually. Okay, this is a set. So if we have a vector space, V is a vector space. Okay, and V naught is a subspace. Okay, then we say x is equivalent to y if x minus y is in V naught. Okay, this is an equivalence relation. Okay, then you take all the equivalence classes with respect to this equivalence relation. That is what is called V by V naught. That we denote it like this, x plus V naught. I mean, that is how it will look. The equivalence class x will look like x plus V naught, right? As a set. Something here, because the difference should be in V naught. This is how it will look. So this is collection of set. Still, it's a vector space. You can add, the addition will be well defined. You just sit and work it out. You can add to the x plus V naught plus y plus V naught equal to x plus y plus V naught. Yeah, it's the same thing. It is just for vector space. Okay, the vector space means there are more structure. It will satisfy all those things. Okay, this is what you just quotient it. Okay, this is what. So here I have to do it there. So now in our case, we take, this is all random variables such that E of square is finite. Okay, then you call L naught equal to all those x such that probability of, I mean, P of x equals 0 is 1. Okay, then you quotient it by L naught. Okay, then you define inner product of x plus L naught, y plus L naught. This is just, I mean, maybe x. Okay, E of xy. This is well defined because this is defined for a representation. I mean, this is for a representative. I mean, this is a representative of the quotient space. This is a representative of the quotient space. Okay, I mean, x is a representative of the quotient space. This is a set. This is a set. You take one element, which is x itself, because you have 0 element here. X itself is a representative there, and y itself is a representative there. Yeah. Huh? V quotiented with V naught. It is just a collection of all those sets of this form, x plus V naught. This is any element is x plus V naught. So, I mean, this is the partition. This is the equivalence class. This is a collection of equivalence class. Okay. No, an element of V quotiented with V naught is x plus V naught. It's possible, no? You can have set with sets. Okay. Now, if you have x plus V naught and plus y plus V naught, you can write it as x plus y plus V naught. This is a well-defined operation. You can check. Because of the equivalence relation, this is a well-defined operation. That is, if x is here, I mean, because anything V naught will again go into V naught. This is a square bracket, which I am writing it as x plus V naught. Same thing, no? It will be all those x plus V naught. Exactly. Yeah. If you just think about it, this is the square, whatever, the bracket x plus V naught. Okay. Okay. Now you define an inner product on this L by L naught, okay, which we call it as L tilde or whatever. This is all those random variables which are quotiented. I mean, which are, see, here x is equal to y if probability of x equal to y is 1. I can avoid all these things and directly give a proof of Cauchy-Schwarz and do this, because I want to apply Cauchy-Schwarz. That's why I'm doing this. Okay, if you are getting confused, you can just. I'm saying that in this, okay, in this two random variables. No, anything will be like this. No, you have one. You have, see here you are identifying all random variables which are almost surely same. Your part, yeah, this is equivalence relation is exactly that, x equal to y. I'm saying that this will be some x, right? Anything will be like this. It is just an equivalence class, no? Anything will be like this, and anything will be like this also. Both these things are same if x and y are, two things are in the same equivalence class if x is equal to y almost everywhere, except for a region of probability 0. Then x equal to y. So now it makes sense.
Okay, that.
If you don't have to do all this, then I have to give directly the proof of Cauchy-Schwarz, because I want to apply Cauchy-Schwarz, because you said you know that. So that's why I'm doing this. Okay. All I want to say is the following. This is so for this you don't need E of xy is less than or equal to E of x square over half, or you have square here. Okay. To prove this, you don't need, I mean, you can directly apply. I mean, this is Cauchy-Schwarz works for semi-inner product also. You don't need to quotient and all that. Okay. But to say the converse, it is exactly for the converse I need this. See, we have the covariance of xy, which is equal to E of x minus Ex, y minus Ey, okay, which is less than or equal to, I mean, E of x minus Ex whole square times E of y minus Ey whole square, which is variance of x times variance of y. Okay. The converse of the Cauchy-Schwarz, what is the converse of the Cauchy-Schwarz? If the equality occurs, that's what I mean. I mean, not converse. When the equality occurs. So if, let me write the statement and explain to you. Okay. If covariance of xy equal to variance of covariance of x y square. Now this is there should be a square root, no? This covariance of yeah, this is equal to this, that is less than or equal to this. There should be a square somewhere. Square of this. Okay. If it is equal to variance of x times variance of y. Okay. Suppose if this is equal to 0, let me make the statement. Then x equal to alpha y for some scalar alpha. Okay. If you are lost, you tell me. Otherwise, Cauchy-Schwarz says that if in a vector space you have an inner product, okay, if inner product of xy is equal to, is norm x times norm y. I mean, if inner product of xy is equal to inner product of xx power half yy power half. Okay. Then x is constant multiple of that when it is an inner product. When it is not an inner product, that's why we quotient it all that. Okay. So it is in the quotient space, this is an inner product. Okay. So if you don't want all this confusion, what you do is directly you write the Cauchy-Schwarz inequality, which you can do it. So is it okay? Let me just give you a sketch of that. Okay. What I have done is the following. I think the proof works like this. E of x minus k y square, right? I think this is what will work. That is equal to E of x square plus k square E of y square minus E of k times E of x E of right. Okay. Now you take y equal to, I mean, you have to choose k. You have to choose k y equal to what? I mean, you replace y by E of okay, and then k equal to E of xy. So this is greater than or equal to 0 for all of them. Okay. You do this, and then you will get that E of xy is less than or equal to E of x times E of y, E of x square, E of y square. To do the calculation, you will get this. Okay, and E of xy equal to E of x square power half, E of y square power half. You don't need to go through all that inner product and all that. You just do this calculation. Okay, I'm leaving it as an exercise. Take this y, replace y by this, and take k equal to this. Okay.
So I'll clarify what I'm trying to clarify what this. You are saying that we can define it to be a quotient space, and then there's a theorem. There exists a theorem.
No, it's all very clear if you just do it carefully. I'm just saying that you take the collection of all random variables which has the second moment. Okay, quotient it with random variables which are almost surely equal to 0. Then you get a vector space. On that vector space, define this inner product by the same thing, E of xy. You take some representative and some representative. You want to talk about the inner product between this, right? Or x plus x naught or something. You take one representative from one equivalence class, another representative, compute this EXY. That is same for all of the, or any two representative. So it's well defined. That inner product is well defined. Then the Cauchy-Schwarz will imply this, and the equality will imply that. But of course, equality means you are applying for this random variable, x minus ex and other thing. Okay. So this is the theorem I want to say is where I have written. If you have covariance, of these two are equal, the covariance of this is equal to this. Covariance of xy equal to variance of this thing holds, then one is the constant multiple of the other. That's what I want to say. Okay. Since I have missed one class, I can go up to 45. I have 10 minutes more. I'll take 15 minutes more. Okay. Let's prove something interesting. Okay, so this is something new. Okay, so I want to prove some inequality. Actually, it's all very easy, but this is a very famous inequality which is used in several places. There are many other inequalities which we will not prove. There are better inequalities, but this is enough to prove what we call as weak law of large numbers. Okay, that's what we will prove now. Okay, we'll prove strong law in the next class. If I have time, I can prove it now. Okay, the proposition is the following. X is any random variable, then probability of x mod x, or x is positive random variable, then you don't need mod. Okay, mod x greater than k, okay, is less than or equal to E of mod x by it's very easy, clear, I think. So I write it in such a way so that we can later have the same proof for continuous random variable also. If I have to write it through density and other thing, it will only hold for discrete random variable. So I write it in such a way, I hope you can understand. Okay. So we have that k is greater than 0. Okay. So we have x equal to x such that mod x less than or equal to k. Sorry. I mean, first we have this. Okay, mod x. We have in some region mod x less than k, and we have some region where mod x is greater than k. Okay, so they add up to 1, of course. This is the, what is this? This is the indicator function. I mean, this is my notation. Did I say that? I say this, no? So this is my notation. This is a random variable. This is a function. Okay, you write that, or you use I. Okay, that's better. Indicator function. I think I used I. which is equal to constant function 1. This is okay. This is a random variable which takes this value 1 in this set, 0 everywhere else. This is a random variable which takes the value 1 here, 0 everywhere else. So either x has to be less than k or greater than k. These are the two possibilities. So if you add these two functions, you get 1. Okay. So if you just multiply by x, you get x. Okay. X times this is x. Okay. Now it's clear. Okay. Now, if you want to take mod x, you can take mod x here. Okay. Okay. Now, expectation of mod x. This is function is greater than this. So expectation of this is greater than this function, right? Okay. Correct? So I put mod x here. Mod x times this is, I mean, I have written 1 as partitioned the 1 with this, and then I have just written it. So E of mod x equal to E of, on this set, mod x times identity of mod x less than k plus E of mod x, right? Indicator function of, I mean, this is a random variable. We are just multiplying mod x greater than or equal to. Okay. Now this is positive. That is mod x is positive. Everything is positive. So this is certainly greater than or equal to. Indicator function is a function. Given a set, it takes the value 1 in that set. Outside that set, it is this. This is mod x greater than or equal to k is a set contained in omega, which is sitting somewhere. Definition, no? Domain is omega. You can define it on any set. Here it is defined on omega because this set is all those omega in omega such that this happens. This is our short notation for this. I fixed it long back. When I write like this is all those omega such that x of omega is greater than k, which is a subset of omega. Indicator function is a function defined on that omega, our probability space.
Indicator, you write capital X.
This is capital X. What is where? This is all capital X. Here. No, this is x is, you want omega. This is just the variable, which is the independent variable domain, where the domain variable. Okay? I don't need this. I shouldn't have written it. Okay. Now E of this is something positive, so you don't care. Okay, only this you care. Okay. So that is E of, but here E of x is greater than k. So that whole thing is greater than this. So k times expectation of just this I. But then in expectation of a indicator function is just probability of that set. This is equal to k times probability of mod x greater than or equal to k. We have proved. This is very easy. Okay. This is really nothing. Okay. Now, corollary is, I think one of them is called Chebyshev inequality. Chebyshev. That is expectation of, probability of mod x minus ex greater than or equal to some number delta. Okay. This is less than or equal to E of x minus ex power k divided by delta power k. Okay. Chebyshev. I think Chebyshev spelling is correct. Okay. Somewhere people used to write FF or something. So I've just restated the whole thing. This follows because since this set is same as this, right? X minus Ex greater than or equal to delta is equivalent to saying X minus Ex is greater than or equal to delta power k. This power k is greater than delta power k, right? It's the same thing. This set is same as where this happens. And if you use that, you get this, right? That's all. There is nothing in this. Okay. Now we prove weak law of large number. Theorem. Call it theorem. Weak law of large number. This is the justification for doing probability. That is, if you have a experiment which you call it as a random variable, you do the experiment enough number of times, then you will get the result very close to the mean. Okay, that's the, I mean, you do the experiment. There is something called probability is defined through what is called relative frequency. You toss a coin. Suppose if you have k number of times heads in a n number of tossing, then k by n is the your probability. You assume that is the probability, right? So that definition is, I mean, that assumption is justified here. That is, if you do the experiment independently, some several number of times, some whatever is, I mean, the number needed will be given by this law, okay, by an inequality. If you do enough number of times, you will get your the relative frequency very closer to the mean. Okay, that's what it means. So this is x1, x2, x3 up to xn are independent random variables. That is, you do the same experiment again and again independently. We independent random variable with same distribution. That is IID, which I call it as independent, identically distributed independent random variables. Okay, independent and identical distribution. You call it as IID, but I have written it. So they are independent random variables with same distribution. Okay, let Sn equal to x1 plus up to xn divided by n. This is the relative frequency. Okay, number of times something for omega occurs and divided by n. Okay, then probability of Sn, sorry, Sn is that, sorry, Sn by n. Sn is that, and Sn by n we want to consider. I mean, Sn is the sum. That is the usual notation. Okay, Sn minus with the same distribution. So let Xn are with mean. Let's just calculate mean, mu, and let's assume that it has the finite variance. It's not required, but in this proof it requires. Later we may prove something better with variance sigma square. Okay. So you have n identically distributed independent random variables with mean, mu, and the variance sigma square. Okay. Then we consider this. Let me write here. Then probability of Sn by n mod of this minus mu greater than or equal to delta. Delta is some small number. Delta is greater than 0. Okay. Is equal to, I mean, I'm actually giving the proof rather than this goes to 0 is the theorem. Okay, for all delta, but this is equal to, I mean, expectation of okay, this goes to 0. This is weak law of large number. Okay, for all delta. I mean, in probability, this is what is called convergence in probability, convergence in measure or something. So I have taken n random variables with the same distribution, mean, mu, variance sigma square. Then I summed it, which is Sn by n. Okay. I mean, what I mean is, sorry, You have endlessly going on. Yeah, the n will go okay as n goes to infinity. Okay, this is okay. I mean, you have countably many IID random variables. Then the probability, so Sn is the sum up to n. The Sn by n minus mu greater than or equal to delta goes to 0. The proof is immediate. So this probability of Sn by n minus mu greater than or equal to delta is just variance, I mean expectation of, if you wish, expectation of Sn by n minus mu square, right, delta square. Okay. But then this is just variance of variance of x1 up to n by n. So this is, they are independent. So you can take the constant out. This, sorry, less than or equal. Okay. This is equal to variance of, variance of Sn equal to, it has n of them, no? Yeah. Yeah. So which is just n times variance of xi, but you have n will, that n will come out, constant will come out a square. So it is just that is sigma square by n delta square. These are constant, so this goes to 0. Is okay. I have just applied this inequality, immediately we get it. But this provided the second moment exists. This is weak law of large numbers. I think I will prove strong law in the next class. So it is just the convergence. This is what is called convergence in probability. We can have almost sure convergence, that will be stronger law.